Good morning or good afternoon, ladies and gentlemen. I'm Makoto Noda of SoftBank. It's quite a pleasure for me to have this opportunity to sharing the latest use case of our Ichimil service. And I'd like to appreciate MGA and especially Kobe-san for inviting me for this conference. Thank you so much. So let me start my presentation. So today I'd like to introduce our latest use case of our high accuracy positioning service, Ichimil. So I'm Makoto Noda from SoftBank Corporation, and I'm at the position of Vice President of Enterprise Business Unit and taking charge of the solution engineering, including this high accuracy positioning service. So super digital society is coming, and IoT world is coming. So that's the background. And in such a situation, automation is indispensable for in each industries like automobiles, drones, construction machinery, or agriculture, or buses, trains, and so on. And then, so accurate positioning data is also absolutely essential for autonomous vehicle or smart construction or autopilot and smarter agriculture also. So, that is the background, the reason why SoftBank started high accuracy positioning service. And we constructed our original control points about 2 years ago, November 2019. And here is the introduction video. So please see this video.
Today, car navigation systems and map apps are essential for life on the go. Discrepancies of a few meters, however, are commonly observed among the current positioning methods. Centimeter-level accuracy positioning service Ichimil, provided by SoftBank, will solve this problem. By using Ichimil, correction data generated by information can reduce positioning errors to the centimeter level through the use of SoftBank's unique control points. Here, control points are key to deliver this service. SoftBank provides this service nationwide by installing reference stations along their cellular base stations. The handover technology that automatically switches neighboring control points enables stable and accurate positioning even when moving over long distances. In addition, due to overlapping coverage across control points, it is possible to continue providing service during issues and maintenance. Not only that, SoftBank offers a compact GNSS receiver at a low price. You can save through an initial introduction discount and use the service right away. Ichimil realizes automatic operation where accuracy and redundancy are indispensable. This will contribute to the wider spread of businesses with a small number of people by automatically utilizing a range of equipment such as agricultural or construction machinery. It could also monitor infrastructure such as roads and dams. Subtle misalignments that are invisible to the naked eye can be found, which will greatly contribute to the safety of our society. In the near future, the service will be provided to more familiar devices, such as smartphones and wearable devices. SoftBank aims to realize an automated and efficient society by providing centimeter-level accuracy positioning service Ichimil nationwide, while also providing GNSS receivers.
And so this slide shows how it works. We SoftBank developed our original RTK base station nationwide. Total number is 3,300 in nationwide in Japan. And they also developed correction positioning core system, which generate correction data and distribute to the receiver rovers to anywhere in Japan. That is the what we are doing as a service in Japan. And our service feature is kind of one-stop service. We create the infrastructure of the RTK-based station network, and also generation and distribution of collection data. And we also provide a device and web user interface to our customers. Web user interface like this. So our customer can monitor current position and the trajectory of the device on smartphone or any PC. So I'd like to introduce use cases in Japan. And we started our service 2 years ago, and Ichimil already have achievement of the contract and the POC from 500 of company and organizations, like self-driving cars and agriculture, constructions, surveying, ship, map, drones, or something like that. So number one is transportation, autonomous driving, and driving assistance for buses. And one local government is operating this kind of the autonomous driving local buses using Ichimil. Okay. And next one is mobile robot. Mobile robot with just a few centimeter errors is also other application of our Ichimil service. And the third one is drones. And there are so many drone use cases. And I'd like to introduce our logistic usage of the drone. And we also have introducing video on this one. Please see this one, please. Sorry, the voice is Japanese, so please read the subtitles. 日常生活がより豊かになります。例えば鉄塔点検では、これまで人が高い場所に登るような危険を伴っていた作業を人に代わりドローンが自動で行います。防災では、災害発生時に人間が近づけない場所をドローンが飛行し、河川氾濫や道路寸断などの危険な状況を把握します。物流ではこれまで車や人が輸送していました。こうした物を運ぶ物流にもドローンが活躍する時代が到来します。これにより道路の渋滞緩和にもつながり、時間も正確に到着します。たくさんのドローンが行き交う時代の到来、そのためには衝突することなく正確に飛行する必要があります。これを実現するための基礎的な技術として誤差なく正確に飛行する高精度測位を使用します。この技術は順天頂衛星導きなどの衛星から受信した信号を利用してドローンの正確な位置を測位することで誤差数センチメートルの飛行を可能にしています。今回はこの技術、ドローンに高精度測位を使用した実際の事例として物流ドローンの取り組みをご紹介します。実際の飛行場所は自然とともに生きる町、和歌山県西室郡すさみ町。出発地点の漁港では専用の箱に重さおよそ5キロのカツオを梱包し、全長 2.3 メートルの大型ドローンへ取り付けます。ドローンは漁港を出発し、配送先である道の駅すさみへ向けて自動で飛行を開始します。飛行中は事前に設定したルートと実際に飛行しているルートをリアルタイムに比較し、誤差を自動で補正します。この技術により出発地点から到着地点までのおよそ3キロの距離を誤差数センチメートルの精度で飛行することができます。到着地点に近づくと誤差の補正を繰り返しながら事前に設定した場所に正確に着陸します。到着したカツオは鮮度が保たれた状態で厨房まで運ばれ、その場ですぐに調理されます。このようにドローンを活用することで漁港から直送された新鮮な魚をさまざまな場所で楽しむことができます。今回ご紹介した物流のようにさまざまな最先端の技術を掛け合わせた生活インフラをソフトバンクは日常生活の中に登場させていきます。こうした技術はあらゆる産業の DX、
スマートシティ実現に貢献し、人々の生活を豊かにしてくれることでしょう。ドローンがあなたの日常で力が感じる時代がすぐそこまで来ています。
And this is another application on drones and used for inspection and disaster support also. And utilization for infrastructure inspection and agriculture and construction site. That is also a drones application. And this is agriculture robot and using HML. And those agriculture robots can be operated under plastic greenhouse and under trees also. It is very precise controlled machines. And this is the construction application and utilization for simple surveying work and also history management at the construction site. And this is other side of the construction application and the aerial work and the safe crane maneuvering and the automation and labor saving on mining work and the road roller compaction management or something like that. And this is other application utilization for streamlining the efficiency of the soil volume calculation and the progress management in civil engineering work. And also ship, hull position management near the harbor and the operating support utilization for autonomous driving for ship. And this is also other one, infrastructure monitoring. So detect changes for disaster prevention by 3D positioning. And this is the utilization of high accuracy positioning data. It's like some kind of future type of application we are now thinking. So one is agriculture field, work productivity improvement and automation using high accuracy positioning. So visualization of the agricultural work and data generation for agricultural work automation using the precise data. And this can also applicable for realization of circular community. So forecast of the agriculture residue early harvest and convert residue into energy or fertilizer. And we would like to realize the sophisticated work by agriculture data. And this is also other cut of the utilization of data for disaster countermeasure. So as I explained, we have 3,300 of base stations in all nationwide in Japan, and the abnormal value of the satellite data can be detected nationwide. So by doing that, we can detect the precipitable waters and detect cluster movement, and considering advanced disaster countermeasures. That's we are thinking, contributing to the disaster prevention by using SoftBank original base stations. And the last one is global challenges. So there is a demand of the worldwide use. So we will enable horizontal expansion of domestic use case by global companies. So we have signed the MOU with uBlocks to start consideration of joint global expansion of high accuracy positioning service. So we are doing our service in Japan, and uBlocks providing the positioning service in Europe and the United States at present. So this is the partnering, and the collaboration with uBlocks, we are doing the global distribution and the device development and the area expansion. That is our collaboration content. So we'd like to make high precision positioning service available to countries of all countries of the world. That is our goal. Thank you. This is all from me today. Thanks.
Okay. Thank you very much, Mr. Makoto.
Thank you.
Next, I would like to invite Mr. Toshiyuki Miyauchi, Vice President, Fundamental Technology, R&D Field, R&D Center, Sony Group Corporation, to deliver the lecture, please. Please welcome.
Okay, can I start?
Yes.
Okay, ladies and gentlemen, I'm Toshiyuki Miyauchi, Vice President of Sony R&D Center. Thank you very much for giving me such a valuable opportunity today. Under the title, Utilization of QZSS and Sony's Earth Mimamori platform for tsunami disaster mitigation, we would like to explain what Sony is working on and its philosophy. I would like to give you an overall explanation, and Kimura, who also belongs to the R&D Center, would like to give you an explanation of our specific efforts. At first, I would like to talk about our thoughts and important points. As you all know, the world is facing many crises. The total population of the Earth is expected to reach 9.7 billion by 2050. Also, the aging society will advance. The working population will decrease. Climate change is particularly serious. A once-in-a-century crisis occurs every year. We cannot overlook the pollution. The Earth is getting dirty. Safe water is also decreasing. In developed countries, social infrastructure is aging, and it is a heavy burden on society. We cannot wait any longer. If we don't solve it soon, it will be irreversible. In order to solve such many problems, we will conduct global sensing. By using sensing technologies, we recognize problems that we have not noticed before, identify specific problems, and take action to minimize the environmental impact and maximize the effect. And finally, we will realize a sustainable future. We call this concept Mimamori. It is a combination of the Japanese words miru and mamoru. As you can see, miru has many meanings and mamoru also has many meanings. These combinations fit our concept very well. Okay, no problem. We hope to protect our beautiful Earth through this Mimamori concept. It provides an opportunity to catch signs of abnormality, issue warnings, encourage action with sustainability in mind, consider what can be done to achieve a sustainable future, and take concrete action. It is important to have a perspective that allows us to see the Earth system beyond human society. Advances in science and technology brought humanity together. However, the Earth systems and human society are not yet connected. It is important to see the Earth objectively through sensing. Now, Mr. Kimura will explain about the specific efforts. Kimura-san, please.
Okay, so hello everyone. I am Manabu Kimura from R&D Center, Sony Group Corporation. It's a great honor to have this opportunity. Miyamoto-san has just explained Sony's Earth Mimamori platform. I'd like to explain the approach to realize this, as well as a proposal for a specific demonstration experiment. Yeah, and as Miyamoto-san explained earlier, human beings are facing various environmental and social problems. Sony is famous for its products such as TVs and games, but the technology behind those products is also effective in IoT. sensors can detect the various events happening on the Earth today, and the AI can translate them into messages that people can understand and communicate them to encourage people to change their behavior. We're focusing on 3 technical areas. The first one is the advanced sensing and the edge AI technologies. It can sense things that human couldn't sense. The second one is the communication technology to correct the sensed information. And the third one is to analyze the corrected information, converted it into valuable information, and provided it to people. And the important thing here is that the solution to environmental and social problems is to install sensors in places that are very far from where people live, such as places where there is no electricity and cellular communication. And a specific example of the first technology is the GNSS receiver. In addition to TVs and the games, Sony also sells this like the GNSS receivers. Are you surprised? And this is a CXD 5610GF, which is a GNSS receiver RSI with dual band support and extremely low power consumption. It is compatible with various GNSS and, of course, Japanese QGSS. Since it supports not only L1 signal, but also L5 signal, positioning can be performed with extremely high accuracy. Recently, digital twin has become a buzzword, and location information is very important in connecting real and virtual world. In the future, a myriad of devices will become digital twins, and we believe that a GNSS receiver with low power consumption will be extremely useful. And the next one is the LTRES, Sony's LPWA communication technology. It can communicate over very long distances, and the power consumption is extremely low too. Yeah, the transmission power is just only the 20 milliwatt. With only this 20 milliwatt of transmission power, 322 kilometers of the communication was successfully achieved. And the GNSS is also incorporated as a standard in this communication technology. Location itself is very important information, but also the LTRES uses the GNSS to synchronize the timing to achieve efficient communication. Yeah, combining these technologies, we first conducted a demonstration of the Mimamori along the coast. This is a place called Miura Peninsula in Japan. It is very close to Tokyo. And we installed an LPWA receiver here and attached the transmitter to the ship and headed offshore. And as you can see, the transmitter is just above sea level. How far can it go? Surprisingly, we succeeded in communicating over a distance of about 50 kilometers, yeah, which is beyond the horizon, error-free up to 40 kilometers. This is a very surprising result, we think. And this means, for example, that if a buoy capable of the sensing tsunami is installed at a location 40 kilometers from the coast, that information can be transmitted directly to the ground. Yeah. And if the LTRES can communicate over such a long distance, what happens when it points upwards, we thought. We launched a receiver to the International Space Station for an experiment. You can see the Japanese laboratory Kibo. We installed an experimental receiver device at the end of this. It was able to receive signals at the International Space Station, which is more than 400 kilometers above the ground. And again, it only has 20 milliwatt transmit power. This is actually surprising things. This means that we can correct the GNSS positioning and sensing information from low power devices anywhere on the Earth. And we did an experiment in Thailand. Jisa-san, really thank you very much for your cooperation in this experiment. A transmitter was installed on the SIP and Andaman Sea, and the experiment was conducted when the International Space Station passed by. We were able to get information about the sea, ocean without using cellular and other terrestrial communication infrastructure. You can understand that what this means. In other words, you can get information about the ocean buoy, and it means that the danger of the tsunami can be detected quickly. And finally, we will introduce also the Sony's GNSS tracker. Yes, Sony already commercialized these things. It is called AmuLink. At this moment, it is sold only in Japan, but I hope it will also be sold in Thailand and other Asian countries. And it has the same processor as Sony's Presence microcomputer board. This processor also has GNSS capability and can receive QGQSM messages from QGSS. This means that there is already commercial level QGQSM receiver. This equipment is capable of LTE communication, but above all, it is important to be able to receive disaster hazard alerts by decoding QGQSM messages, even if they are outside the cellular range. I explained the mechanism to detect tsunami before, but we need to tell people the information we detected. The combination of the QGSS and this QGQSM receiver makes it possible to alert people to danger. This slide is my last one. As I explained, I believe that the combination of the QGSS and the Sony's memory technology will enable a variety of memory things. We will be able to do cost-effective tsunami monitoring at the coastal level of memory. And at the national level of memory, it will be possible to monitor the tsunami in the ocean. And it is also possible to implement the tsunami warning system using QGSS and memory for people. Thus, the combination of QGSS and Sony's memory technology has great potential. We have to contribute to society by conducting such experiments in Thailand and other Asian countries. I'd like to return the speech to Miyagi-san. Yeah, thank you.
Mr. Kimura, thank you for your explanation. Yes, we will, with Sony, will do memory to achieve a sustainable future. To realize the memory concept, we are working on various field work. We will drive our efforts to develop and integrate innovative technologies. As Mr. Kimura explained, we hope to conduct a series of demonstration experiments in Thailand. Let's work together to protect this precious earth and build a sustainable future. Thank you very much.
Oh, sorry. Okay. Thank you very much, both speakers from Sony Group Corporation. Next, may I invite thank you very much, speaker from Sony Group Corporation. Next, may I invite speaker Renosuke Ishikawa, assistant manager in NGT to deliver the lecture. Please welcome.
Good afternoon, everyone. Can you hear me? Good afternoon, and maybe it's still morning out there. I'm Ryunosuke Ichikawa from NTData from Japan. Thank you for inviting us to this conference. This is my pleasure to have this occasion to present data here. Today, I want to introduce about our project that about EWS early warning system by using QGSS, and we're going to have a demonstration experience on this project in some Asia Oceania countries. So I hope everyone interested in this project. This is the agenda. First, I will explain about the background of this project, and next, I will introduce about our project, and after that, introduce the example solution in Japan and future possibility to various fields, and after that, our future plan in Asia Pacific region. So the first is the background of this project. Japan has Michibiki satellite that is one kind of positioning satellite, but it also have EWS function. And we're going to expand that function and make that function open into Asia Oceania region. And the project is led by Cabinet Office Japan. The targeted area is wide, that the satellite orbit is going to north to south and withdrawing like number 8. So the countries that can receive radio wave from the satellite can be the target of the service. And the next one is, this is the image of the system that we are going to create. The first, we are going to develop the message generating software, and the software will be provided at the control station on the ground, and it will be the organization like local government or national disaster prevention organization. And after that, the government make a message from the software and send a message to Michibiki satellite. And the satellite send the radio wave to the tower on the ground, and the ground can make a sound from speaker. And we're going to make a system by spread the message by LPWA, low power wide area network. And the LPWA network to relay the EWS message from QGSS. And after that, the message will go to the terminal device to the residents and here. And the terminal device can alert the message to the residents. And about this project, not only entity data, but also several leading company or institute like Keio University and geospatial companies like PASCO, Asia Air Service, and Asian Disaster Reduction Center is also involved to this project, and we are going to make this project useful. This is an example solution in Japan. Actually, we provided a solution in Japan, and I will introduce for that, for example. It's kind of same that we are going to bring it to the overseas on this project, but we believe this system is matched to countries in Asia, Oceania countries more than Japan, because the system, it used the Michibiki satellite here. So it will not affected by disaster damage on the ground. And the government of the countries don't need to launch the satellite by themselves. Japan owns the satellite, and so it have a cost merit. And also the message will be spreaded by LPWA, so it is easy to distribute to wide area with low power. And in future, LPWA can have more utility in many fields. For example, water level monitoring, landslide monitoring, and also for agriculture field. And the situation is matched to send a small data, not large data, but send a small data from the place where the internet is weak or not prepared. And the data sent to the relay devices and go to the municipality or the server. And this is the future plan in Asia Pacific regions. You're planning to conduct some demonstrations in Asia Oceania countries. We want to use this system to combine to the existing warning system at their local government and make it easier, make the system easier, or make the system more useful, and or use this system as alternative of the existing system. And if anyone at here were interested in this project, please don't hesitate to let us know, so we can cooperate with that and ask the existing system and combine with our system and make the system more useful. Thank you for your time and attention. Thank you very much.
Thank you very much, Mr. Kishikawa. And now may I invite the next speaker, Mr. Bono Sadano, International Sales and Marketing Manager, Michelin Systems Japan, to deliver us the lecture.
Hello, good afternoon. Thank you for having us in here. This is the presentation from Michelin Systems Japan. Unfortunately, like this year, we cannot go to Japan. We cannot go to Thailand because the Corona situation. But we really appreciate the help from the Cabinet Office, especially Mr. Kogure and Ms. Yoko, to help us in having this kind of opportunity to present what's the improvement and the success case that Michelin Systems Japan has been doing for the past year. Just a briefly introduction, we have been a long partner in the MGA, so just refresh a little bit. Michelin Systems Japan is located in the Osaka, and then we are more on the R&D company, and then we have like 24 engineers, and we also have the branch office in the Moscow. Major activities, we are providing the high precision GNSS solutions, and we are utilizing the QGSS in the Southeast Asia. I'm from Indonesia, and then I think that's the best ground for us to do the testing of the QGSS, and we are been doing the promotion for the QGSS as well. And also the important part is we need to monetizing all the satellite into the business, right? Okay, so just just to do some review, actually, the good things has become the last speaker because the previous speaker, like from Mr. Ichikawa from the NTT, already helped us to present like what's the QZSS and then all the orbital thingy. So like just to recap, maybe I will use this slide. Yes, in Japan, the QZSS can broadcasting the SILAS and the Madoka, but outside of Japan, we are focusing on the Madoka. So like in Indonesia, in Thailand, and in Philippines and other Southeast Asia country, can we get the QZSS? Yes, first using the post-processing, second is using the internet connection. But from our technology, we are utilizing the L6E from the QZSS, and then you can access the real-time PPP. Okay, so that's the benefits of using our technology. And then to validate this one, like we've been working with all the institutions in Indonesia, like the big university and all the research institutes. Later on, I will go one by one on the success case and on what we have been doing in Indonesia. Okay, so just keep in mind, like outside of Japan, maybe like in Thailand, Indonesia, Singapore, and other country, it's using the real-time PPP from the Madoka. Okay, so before touching the success case, like it's better to refresh a little bit what is our product line. Okay, so the first one, like we launched the first generation on the 2017. It's like the EVK box, and then the dimension is quite huge. And then for the second generation, it's a smaller, and then with the low power consumption. And then now we are ready to launch the third gen, which is the digital ASIC. And then it's only size like 9 × 9 millimeters. And then it's very much like low power consumption. And then what we are going to do with this, so please stay tuned. And then like you can contact us, like what we have been working for the final products. We will let you know later by the end of the Q2. Okay, so this all the improvement that we are been working for the past years. And then in terms of core technologies, like we can separate our technologies into 3 parts. First is like the self-initializing base station. Okay, so just to refresh, like if you want to do the RTK, first we need to have the base and the rover, right? So the problem with the moving base stations is like you need time to set up. But with our technology, like for example, there is the obstacle. You can just move the base to the other place and then you set up for several times. And then it can transmit the correction data to the rover, which is very useful in terms of like prevent the obstacles in the tall building or in the forestry. Okay, so that's the first our core technologies. And then the second one, maybe as you guys know, that we are good in do the machine control, which is like the autonomous solutions. And then it's all utilizing the real-time PPP from the QZSS. And then the recent update that we have been doing, we have the dual antenna solution for heading. So this one, it's happened in Japan just a couple weeks ago. It's all autonomous, and then it can find the heading like which is facing the north, and then it can docking automatically without any interference of the human. It's just like purely the positioning. As you can see, this is also can be applicable for the dynamic positioning, like in the marine application. So when the boat has been swayed by the wave, it can go back to the original position. As long as you lock the coordinate, it can just go back again. Okay. So again, in terms of the technology, like I think we are also quite leading in this area. You can see it's like manage to dock, and then they're all happy. Okay. So okay, so I will just go for the application. Before that, thanks to the Cabinet Office for tidying up all the success case for the QZSS application in Southeast Asia. I get the pictures and all the information from their website, so feel free to visit their website. It's all in Japan, but you can use the Google Translate and then translate it into English, right? Okay, so the first one is like, I will divide it into the surveying parts. The first one is like, I will start on the upper left, right? So the upper left part is for the, this is happening in Indonesia actually, like they are doing the monitoring on the reference point. Okay, so in Indonesia, like every year there is the slightly positioning change on the reference station because our tectonic planktation and all those things for the frequent earthquake, it will cause the shifting. So we need to regularly maintain. Like I mentioned before, if we use the RTK or we use the total station, it takes time, and then like it's really not efficient. So that's why the Cabinet Office Japan work with the local institution, which is called the Geospatial Information Agency. Mr. Arif is the leading leader and the researcher. I think he also joined the event. Thank you so much for your help and support. So we are managed to measuring all the reference point in Indonesia. Okay, so like it's fast, it's accurate, and then the data can be used in order to maintaining all the reference station in Indonesia. Sorry, reference point in Indonesia. Okay, so on the right side is for the land survey. We are having the company that utilizing our receiver box, and then they built their own software in order to again change the RTK method into the PPP, real-time PPP. And then of course it will give you the high accuracy and also fast. And then on the left side, the bottom part, it's the soil measurement system by the Hitachi. It's happening in Australia. So just again, they use the software and then they can measure all the volume of the soil in the accurate quantity. And then also for the seabed mapping, it works with the echo sounder, so it can give you the accurate positioning of the floor plan. Sorry, seabed floor plan. Yeah, of course, like on the sea, you cannot use the RTK, right? So you need to use the PPP. So that's why MSJ can step in and then say that, hey, I'm the one who has the real-time PPP. So you don't need to do the subscription like the other DGPS have. For example, like the other brand, so they have the service too, but you need to pay monthly subscription. But for us, thanks to the Cabinet Office Japan and then all the Japan government, we have the satellite correction is free, and then you can use it 24 hours, right? So it's quite really useful for the sea or the offshore application. Okay, so moving forward for the machine control, or like the automatic lawn mower, and then also the unmanned surface vehicle with the depth sounder, again, is all the autonomous solutions. Okay, so for the other application, also like we have tons of the application. Actually, like the application came out from the institution that bring this idea to us. Like, hey guys, I have this case. Can you solve it? Oh yeah, we can sit down together and then we can work together. So that's why we want to say thanks, like for several institutions in here. Like it's all from Indonesia because I'm from Indonesia, but not close the door for the researcher from Thailand and other country in the Southeast Asia. Feel free to contact us. Okay. So all the information can be done and can be accessed through this one. Okay, so that's all for my presentation. If you have some question, just let me know, and then feel free to contact me or contact our website. Thank you so much for your help and support.
Thank you. Thank you very much, Mr. Sadono. And now I would like to invite the last speaker of the morning session, Professor Dr. Ponchai Sapniti, Director of Thai-GNSS and Space Weather Information Center, King Mongkut Institute of Technology, Lat Krabang, to deliver the special lecture on high-bridge equatorial plasma bubble detection and effects on positioning navigation systems.
Hey, good morning, everyone. Can you hear me well?
Yes, sir.
You can hear well, okay? Okay, first I'd like to thank the organizer of the MGA 2022 for inviting me for this special lecture. My name is Professor Ponchai Supanithi from the Faculty of Engineering and also from the Excellence Center in GNSS and Space Weather at KMITL in Thailand. And so here's the staff in my team that we work together. There are 5 professors and there are some graduate students who contribute to many projects over the years. So let's see. The problem that we are focusing on is the study of the equatorial plasma bubble, or EPB, and also how they affect different technologies, especially in positioning and also in navigation. Equatorial plasma bubble is a depletion of the plasma density in the ionosphere. So the region that we are interested in is in the range between 200 kilometers from Earth up to over 1,000 kilometers from Earth. And this depletion of the plasma density in the ionosphere, that is so-called EPB, it is due to the instability at the bottom side of the ionosphere. And it is well known that it typically occurs at the equator region and then expand to the higher altitudes. Additionally, we also know that the EPB tends to move from the west to east. So from this picture, this is the picture of the ionospheric electron density gradients, and with the utilization of the GNSS signals, we can analyze these type of maps, for example. There are various ways to study the EPB, and the EPB causes different phenomena on the GNSS signals. For example, with the disturbance in the ionosphere, we see amplitude and phase scintillation, so-called scintillation, for example. And in order to study this EPB, there are various instruments that can be used, one of which is the ionoson system, which emits the radio wave continuously to the bottom side of the ionosphere. So this is the bottom side. In some system, we can also study the in situ signals with the in situ sensor from the CubeSats or from the LEO satellites, for example. Of course, we can also utilize the GNSS signals to study this type of, to study the media, the disturbance itself, and also study the fluctuation in the GNSS signals. And recently, we also utilized the system so-called VHF radar that penetrates up to almost 1,000 kilometers in the ionosphere and sends back the echo, and then we can analyze various phenomena as well. So let me refer back very briefly. We started working on the project with NICT Japan back in 2005, and the project that we participated back then was so-called Sea Lion Project, or Southeast Asia Low Latitude Ionospheric Network. With the purpose is to monitor and then forecast this type of ionospheric disturbance, especially plasma bubbles. And if you look on this side, this is the map of the world, and the very bold red line represent the magnetic equators. So the ASEAN region is in this area. So it is very unique observation network that has the conjugate observation points at the southern and the northern hemisphere. And back then, so basically we work with different countries looking at this study. And back then we started with using the ionoson station and also the GNSS station as well. So, so today, nowadays, at the moment, we are operating various instruments around Thailand with the GNSS receiver, ionoson receiver, also the satellite beacon receiver in Thailand and also in Vientiane. And in 2022, we will expand to Phnom Penh in Cambodia. And all this data will come to our server at the university, and then we analyze this data, and then we provide the data products on our Thai GNSS and Space Weather Information Center. And please note that this web portal, we work with various partner universities and also various researchers as well. You're welcome to look at this web page that has different information from the observation and also data products. But I will talk briefly about some data products and some results that we have. For example, here, this is one of the data products that we provide each day. This is daily TEC plots. And TEC is actually, it stands for total electron content, or is the electron density. It is computed from the GNSS pseudo range from two frequencies. And for example, if we take a look, we can see that the top, these are the stations. And so the top figure here, you will see the blue curves. So these are the vertical electron content, which can be translated into the vertical delay that can be used in positioning. And the bottom figure here, it represents the standard deviation of the change in the electron density, which is so often called ROTI, or the rate of DC change index. So what it is when utilizing the GNSS signals, it will indicate the anospheric disturbance for the L1 frequency, for the L5 frequencies, for example. This is an example of the map that we generate on the website. This is daily data product. The top one represents the TEC map, or the delay map in the ionosphere. And the bottom one represents the disturbance detection. Whenever you see the red color, that means we see the disturbance. We also expand further to a larger region, not only in Thailand, but also in ASEAN as well. So you're welcome to visit the website to look at these products. And we have historical data product that you can also download and also take a look at as well. Another issue that we look at is scintillation. Scintillation is the amplitude and phase fluctuation in the GNSS signals that will play a role in the positioning and navigation directly. So whenever we see this fluctuation, then we will see this type of the change, quick change, rapid change in the amplitudes. And in the worst case, it may cause the loss of lock in the GNSS signals as well. So this is an example of the result from the Bangkok station that we look at the scintillation index, so-called S4 index, at the L1 frequency and the L5 frequencies. And we found that both in the GPS system and also in the Galileo system, for example, the severity on the lower frequencies, such as the L5 frequency, is more evident than the L1 frequency, for example. Then these are some of the plots of the S4 index, which shows the scintillation for different days back in 2020. And we will see this type of shooting up of the S4 index all over the place. So we do analysis and do statistics of this type of results. And this is particular for the local disturbed days due to the equatorial plasma bubble. But then it turns out that not only the GNSS system can monitor this type of scintillation, we also have another instrument called a satellite beacon receiver. And in this project, we work with NICT and also in Kyoto University as well. So what we do is we have two types of receiver. One is the GNSS receiver, and the other is the satellite beacon receiver. So we try to analyze this S4 index, or scintillation occurrence, between the GNSS and beacon satellites. And one of the results that have shown is that, so there are different cases. It's not always that so for example, if we look at case one, in case one, we see the scintillation that occurs at the beacon satellite and also the GNSS system. Please note that for the beacon satellite, we are looking at much lower frequency at 150 or 400 megahertz. But for the GNSS system at L1, for example, it is at over 1 gigahertz, 1.5 gigahertz, for example. So there are different cases that we look at. For example, sometimes the scintillation occurs in both signals. Sometimes the scintillation occurs in the beacon satellite signal, which is represented in the lines. But then we may not see the scintillation in GNSS signals. On the other hand, if we look at case two, for example, we may not see the scintillation at lower frequency, but we see at the GNSS system. So if we have more and more data, it will be more and more useful to see how different frequency, how different system can capture the scintillation in the ionosphere. And the reason we look at the satellite beacon is because beacon satellite is because the window time, the visible time of the beacon satellite, because it is the LEO satellite, low Earth orbit satellite. So the window is very short. So we can see the whole sky in 15 minutes. While for the GNSS system, in the whole sky, we can see over 6 hours, 7 hours, for example. So the beacon satellite, in one way, it can give you the spatial resolution, and it has much better spatial resolution when trying to look at this type of disturbance. So both systems will complement each other in this type of scintillation study. Next, another project that we also work with NICT Japan, which is we generate the actual ionospheric delay correction and compare with the broadcast Klobuchar model correction. We generate the daily positioning error map over Thailand. This is an example for the single point positioning. And you can take a look on our website that it shows both the horizontal and also the vertical errors. In the future, we want to expand this map from the single point positioning to RTK system, for example. Here is another result. This is the effects of the EPD on the RTK positioning errors. For example, we look at the date of year 59 in 2020, and also day of year 292, 2020. And you can see here that when we look at the position error of the RTK, this is the vertical positioning error. This is the horizontal positioning error. We see very huge fluctuation in the errors that occurs on these days. And on the left-hand side, these are the plots from the TEC and also for the ROTI, which we use to select the dates. Okay. Another project that we work on is on the effects of the plasma bubble on the navigation in airplanes. And here we work with the Electronic Navigation Research Institute in Japan and also Aerothai and also the CAAT Thailand as well. So in this project, what we do is we set up the baseline system with 3 stations around the Suvarnabhumi International Airport. And we're trying to see how the equatorial plasma bubble affect the spatial gradient of the ionospheric delay and how it affects the performance of the landing system, such as GBUS system. And this is an example. We look at the delay gradient between stations around the airport. This is the east-west direction. During the disturbance, we see a huge jump of this the gradients. Similarly, for the north-south direction, we also see these gradients as well. And it will the application is to analyze this data and then send the statistical information to the airport, to the authority, so that they utilize the actual values that reflect the local conditions. This is an example. We also analyze the delay gradients during quiet time, disturbed time, during solar maximum in 2012. And we show the occurrence and the high value of the this disturbance, these gradients during different seasons of the year and different years that we look at as well. And these are also published. Last topic is on the new system that we implement recently, which is called VHF radar. So this system is a big project together that we work with NICT, Nagoya University, and some other partners. And it's a huge area with the radar that we invest together with NICT. And basically it detects the fresh bubbles 24 hours a day. And this is an example of the picture that comes out from this VHF radar. At the moment, we use the technology like support vector machine, which is a type of artificial intelligence, and try to detect the EPD presence, EPD speed, and also the directions as well. And lastly, other system can also help detect the disturbance at the bottom side, like the ionoson system that I mentioned earlier. And this is an example of the statistics of the occurrence of the bubbles, but from the bottom side point of view, for different months, maybe it's a bit small, for different months that we can see. This is in 2019, for example. And this is the project that we work together with ASEAN countries. It is sponsored by ASEAN IBO, and basically it's a capacity building, joint research, staff exchange with different countries. And the project is related to GNSS and atmospheric data products for disaster prevention and aviation. And lastly, we have just been funded by the Ministry of University and Research to construct the Excellence Center in GNSS and Space Weather. Okay, and I think that's all I have. I will overview about our research work. And if you have any question, you're very welcome. Thank you very much.